to introduce Colin. He's been in the research group for 5 years. I'll say a little bit about what he did in the first couple of years, because I don't think he's going to talk about it today. Colin started out working on dye-sensitized solar cells, and he and William Nguyen wrote a couple of nice papers. But then there was a discovery that sort of rocked the world of solution processed solar cells when the Perovskites were discovered, and Colin was one of the first in the group to help us make the transition to using those materials. And something we've wanted to do for a while is figure out how to make inexpensive tandem solar cells, and that's what we'll talk to you about today. These are complex devices. There's one solar cell stacked on top of another, and so that you might say there's twice as much work to make them as with ordinary solar cells. And Colin has really done a lot to work with a lot of different people to pull everything together so that these structures could be made. We knew other people would want to do the same thing, so the competition was pretty intense, and we heard the rumors, and we knew who our competitors were, and they were people we'd rather not have to compete with. But Colin pulled it off, and I'll show you a couple of seminal papers today, the first 4-terminal Perovskite tandem and the first 2-terminal tandem. For that work, Colin and I were invited to write a review article for the MRS bulletin. So this is the August issue here, all on perovskites, and it's got his review. And he also won the Bob Huggins Award for the best research in the material science department. I believe that was the year before you won that award. So with that, let's welcome Colin to
Thank you, Mike, for the kind introduction, and thanks everyone for being here to listen to me talk about what I've been doing. Before I get into what that actually was, I'd like to take the time to thank everybody who is instrumental in me being here today. So I'd like to thank my family for being here. They finally get the chance to figure out what exactly it is I've been doing over the last 5 years. I'd also like to thank people out of the McGee group who kept me sane during my time at Stanford and got me out of the lab when I might have just stayed in it. And I'd also like to thank collaborators from MIT, EPFL, Oxford, and the National Renewable Energy Lab who were instrumental in all of this work I'll talk about today. And finally, thank you, Defense Committee, for being here today, taking the time out of your busy schedules. So thank you, Emma, Yi, Bruce, Tom, and Mike. And finally, I'd like to thank Mike in particular. You've given me a lot of good advice and mentorship over the years. And one thing in particular sticks out in my mind when maybe at the end of my first year, I don't have this email anymore, but we got out of a group meeting and you sent an email and you said, I'm confident that you and I will do the next big thing together. And I don't know if that's something that you just tell all of your but don't tell me. And it served as inspiration. And so we'll leave it to your judgment whether or not this is the next big thing. So today I'll be talking about polycrystalline tandem photovoltaics, and instead of motivating this talk as a why solar, why we should all go put solar on our rooftops, why we should blanket the entire state of Nevada in solar panels, and we can evict everybody from the state of Nevada and build solar panels over their houses, and if we did that, then we'd have enough solar energy or solar power that we could power the world, and that would be great. But there's a reason that people are still living in Nevada and that it's not full of solar cells, and that is that energy or electricity is a commodity, and in a commodity market, the cheapest get there, as you might say. And so hopefully we'll be able to switch the narrative during this talk from why not photovoltaics to why photovoltaics. Now, as somebody who makes a solar cell, I can think of the entire system as being the module that contains the solar cells and everything that is not the module. And this includes things like the inverter, the installation cost, the labor, the land, etc. And we call this the balance of systems. And for most of the history of the photovoltaic industry, the module was the dominant cost in this system. And so this drove a lot of work with reducing the price of the module, and this happened so successfully in China over recent years that about 5 years ago, the equation flipped. And instead of the module being the dominant cost of the system, now it's the balance of systems that sets your system price. And so as someone who makes solar cells, now I can no longer make a large impact on the system price simply by further reducing the cost of my module. Instead, on the y-axis, this system price is given in dollars per watt. And so I can affect the entire system by simply making my module produce more watts and make it more efficient. Now, this is not a particularly easy thing to do. This is the history and a little bit of projection of the typical commercial solar cell module. And a few years ago, it was 14 to 15%, and in a few years, it's projected to be about 16 to 17%. But this illustrates that it's a bit difficult to make large leaps and bounds in the efficiency. But if we suspend reality for a moment, and we take our 2015 system price of $1.80, and we pretend that we can do a couple of things to it. We can either have the module price and keep the same efficiency, where we can save 30 cents on the system, or we can pretend that we can hit this magical 30% red dot in the sky and pay more for the module because we're making it more efficient. And if we do that, then we can affect the balance of systems cost by 60 cents per watt. And so this is hopefully motivation enough that instead of working on making the module cheaper, we should work on making it more efficient. Reaching this 30% magical red dot in the sky is easier said than done. And the curve on the left is the theoretical efficiency of a single absorber-based solar cell. And it can reach 30% theoretically. But this vertical red line is indicative of silicon, which is the most common solar cell material that you can buy solar panels with. And the star there at 25% is the record efficiency that's ever been made with silicon. And many people would tell you that this also represents a practical efficiency, that you will never make a silicon module that is greater than 25% efficient, or at least not in the viable future. And so, continuing on to try and reach this 30% magical red dot in the sky, then our next option is to make a double junction tandem, which means we're using two different absorbers in our solar cell. And there's an area on this contour plot that is a combination of your choice of top and bottom absorbers that gets you to over 40% theoretically in your solar cell. Now, the reason that our solar cells are not already 100% efficient is that the solar spectrum actually spans a very large energy range. So you can do the experiment that you can walk outside after this and you can stare into the sun, and as you're staring into the sun and going blind, you'll see it looks yellowish orange. But in fact, what your eyes are not telling you is that you are being irradiated with UV, visible, and infrared light. The consequence of that is that the goal in a solar cell is to absorb as much of the light from the sun as possible, and then take the current that is generated by absorbing that light and extract it at as high of a voltage as possible. But physics deals us a bum hand here, and both of these are related to the material property in your semiconductor called a band gap. And as your band gap shrinks, you can absorb more of the light coming from the sun, but also as the band gap shrinks, you can extract that current at a lower voltage, and therefore you have that optimization function. The double junction tandem changes that optimization function, where now instead of using a single absorber material to absorb most of the light but generate a small voltage with it, now you can use two different absorbers, one that is a large bandgap solar cell that absorbs the high energy portion of the sun and generates a high voltage, and is transparent to the low energy portion of the sun that's absorbed by a small bandgap absorber below, and extracts that current at a lower voltage. And the efficiency potentials are pretty different between the two. With a tandem, you can get 46% in theory, while with a single junction cell, you can only get 34%. Now, this idea of making a tandem module is not a new idea. In fact, it's been around for decades. And even then, the idea of making an efficient tandem module is not new either. The cell, for example, on the end of this gloved finger is probably somewhere around 35 to 40% efficient. But keeping with the analogy before, the reason that this solar cell is not blanketing the state of Nevada is that it's prohibitively expensive to make. You have to grow it as a single crystal, which means you have to use specialized tooling, and you have to grow it at a low throughput. So what we'd like to do is to be able to not worry about having to grow our solar cell as a single crystal, and instead make it polycrystalline, which opens up the options for things like printing, which uses low-cost tooling and is compatible with high throughput, and those exist too. So this image on the right is of an organic tandem, and this organic tandem has the cost structure that we'd like, but it's probably only about 10% efficient. So our two options on the table that we have right now is either to make something that is incredibly efficient, that is what we want, but is prohibitively expensive to make, or something that has the cost structure that we like, but is prohibitively low in efficiency. And now there's something that potentially bridges that gap. A few years ago, simultaneously out of both Oxford and EPFL, researchers figured out a way to use a material called a metal halide perovskite in solid-state solar cells. This metal halide perovskite that they chose to use used lead as the metal, iodine as the halide, and an organic called methylammonium that served as a spacer in the lattice. And this material, this methylammonium lead iodide, ended up having a lot of advantageous properties for solar cells. First, it was a very strongly absorbing direct bandgap semiconductor, even more strongly absorbing than gallium arsenide. And it also made efficient devices. So this top chart is a table listing the optical bandgap of your absorber material and the open circuit voltage times the elementary charge that you can extract from making a solar cell. And the difference between these can be quantified as an energy loss that is indicative of the quality of the solar cell that you're making. A couple of months ago, the perovskite jumped a couple of rungs on this ladder when the open circuit voltage for these devices improved to as high as 1.19 volts, putting it past its commercial competitors like silicon, SiGs, and cadmium telluride. And moreover, the perovskite makes an extremely efficient solar cell with the certified record efficiency above 20%, which puts it on par with both SiGs and cadmium telluride, which have record efficiencies of 21%. Now, this was only on an 0.1 centimeter squared device that you can barely see with the naked eye, but nevertheless, it provides a proof of principle. And it's also compatible with this low-cost processing that I was mentioning before. This is a video that I got off of YouTube where a researcher took printed down a layer of perovskite onto a glass slide, and right now it's clear because there's still solvent in the system. It hasn't formed the perovskite structure, but after only a millisecond of curing under this curing system, he got rid of all the solvent, and what you're left with is perovskite. And these are all necessary things in order to make a solar cell that is compatible with the low-cost requirements of today's industry. There's one more requirement that has to be met in order for it to be useful in a tandem, and that is it has to pair well with the other absorber that you are going to use. So we're going to choose to use something that's already at scale. We're going to use either silicon or SIGs that has a 1.1 electron volt band gap. And if we were to do this, then we would like to have the second absorber be somewhere between 1.6 and 2.3 electron volts in order to reach this 40% theoretical efficiency contour. And it so happens that methyl ammonium lead iodide is 1.6 eV for its band gap, and so it is an ideal material for using as the top cell in a tandem. To go about then making a tandem, now that we've decided on the materials that we're going to use, we have a couple of different options. We can either go the mechanically stacked route, where we make separately a silicon solar cell from start to finish, and we make a perovskite solar cell from start to finish. And then when time comes to make the tandem, we simply put them on top of each other, and that's the end of the story. The other option is a monolithically integrated tandem, which is the more classical design, and that's what the solar cell on the end of the gloved finger was made using, where you start with a silicon wafer and you engineer in either a tunnel junction or a recombination layer, and you deposit the perovskite directly on top, such that at the end of the day you're holding a single solar cell that has multiple junctions inside of it. The perovskite itself has a couple of options with how you would deposit it. The perovskite is an intrinsic material, which means it works best when you have P-type and N-type heterojunction layers on either side. And there's a choice here which hasn't been fully fleshed out, which is the best choice. You can deposit the N layer and then the perovskite and then the P layer, or vice versa, P-I-N. We'll focus on the monolithic tandem first, and this was in collaboration with researchers out of MIT. We decided to take an N-type silicon wafer and do an ion implantation of the emitter, the P-type emitter, ending up with a classic PN silicon solar cell. And then by PECDD, we deposited an N-type amorphous layer on top and recrystallized it in order to form a tunneling junction in between this N-type layer and the emitter. From literature, we knew that TiO2 serves as a good electric contact between both N-type silicon and serves as a good heterojunction with perovskite. And so we decided to build our perovskite in an NIP style architecture on top. Now we made a few of these tandems, the best of them being around 13.5% efficient, that had a voltage of 1.6 volts and a nice fill factor, both of which were indicating that the tunnel junction was doing its job. There wasn't any voltage loss there, and the the fill factor meant there wasn't any additional series resistance that we could measure by having the tunnel junction. This solar cell was ultimately limited in its photocurrent, and this is because on the right, the perovskite was generating 11.5 milliamps per centimeter squared in that subcell, and the silicon was generating 14.7. When you're making a monolithic tandem, there is a condition that you built into it that the top and bottom cells are connected in series, which means their voltage is add, but also that you're restricted to having the same current pass through both cells. And so even though the silicon was trying to generate more current than the perovskite, that current was basically thrown away. And so, just speaking hypothetically, if we had managed to current match to 15 milliamps per square centimeter, we would have had about an 18% tandem. But the reason that didn't happen is because when we built our NIP style perovskite solar cell, that P layer was spirometad. And the transmission of a doped layer with spirometad is on the right. And you can basically overlay that transmission curve with the gray region in the quantum efficiency plot on the left. and see why the perovskite wasn't getting as much light as we might have wanted it to. So the spirometad layer was clearly not a good window layer, and we would like something that's more in the range of 3 electron volts and doesn't have any of this parasitic absorption throughout the visible and the infrared. So let's pretend that this is solvable and we have our 18% tandem. How do we then go from this 18% tandem to that magical 30% red dot in the sky? And the answer is that maybe it's a little bit difficult to go about doing that, because there is a difference in between how you would like to make a silicon solar cell and how you might like to make a perovskite solar cell. A silicon solar cell, throughout half a century of design optimization, has ended up with a textured top surface and a textured bottom surface in making silicon pyramids. And these silicon pyramids are there because silicon, as an indirect bank gap absorber, does not strongly absorb the infrared light, and these pyramids serve to have internal reflections, so the infrared light can bounce up and down throughout your silicon solar cell until it has a high probability of being absorbed. On the other hand, the perovskite is deposited by solution processing, and solution processing is an inherently planarizing type of deposition, meaning that within these pyramids you will get more perovskite in the troughs and less perovskite on the peaks. And sometimes this is okay, but because we're only trying to deposit half a micron of perovskite and instead we're depositing it on 5 to 10 microns thick of this roughness of the silicon pyramids, the consequence is that on the peaks there is no perovskite at all. And when there's no perovskite at all, then when you finish your device and put the metal on top, then you have metal directly touching your silicon, and that's a short, and your perovskite will not be operating in the way that you want. I'm not saying this is an impossible task to do. It's just certainly very hard. So we can pretend then that this solution will be made, and we can make a 30% monolithic tandem solar cell. And the way that you made this 30% monolithic tandem solar cell was that you engineered it to work under a single spectrum shape. And this spectrum shape is called AM1.5. But then you need to take this solar cell and put it outside in the field. And if we're continuing the going blind analogy, if you walked outside and you stood there for a long time and you watched the sun, you would notice that it was a different color in between when it was dawn versus when it was noon versus when it was evening. And it was a different color versus when it was in the summer versus in the winter, was a different color when it was cloudy versus when it was sunny. And if you moved around a bit, you'd see it was a different color when you were up at the North Pole than it was at the equator. And the consequence of this can be seen in this plot of representative solar spectra in Denver, Colorado, where you can split this plot in the middle at 700 nanometers, where everything to the left of 700 nanometers is what the perovskite absorbs, and everything to the right is what the silicon absorbs. And there's some cases here where the perovskite and the silicon will absorb about the same amount of light. But there's also a lot of situations here where that is not the case, and there will be a current mismatch in between one or the other absorbers. And as was the problem a few slides ago with the monolithic tandem I showed you, whenever you have a current mismatch, then you're throwing away that power. So even though you may have made a 30% monolithic tandem solar cell in the lab, when you put it outside, it's highly unlikely to be anywhere near that number if you average it over the entire year. So with these Achilles heels in mind, how do we go about making our 30% tandem? And the answer is maybe you don't make it from monolithic tandems after all. The other option is to make it by mechanical stacking. And the first advantage of this is that you can keep the design optimization that went into both of the solar cells. So we can keep our texturing on the silicon solar cell, is that the perovskite, the vast majority of the time in the world, is being designed and optimized to work by depositing it on glass. And so you can keep that design optimization as well. And so here is the first generation of perovskite mechanically stacked tandems that we made, where we used a semi-transparent perovskite cell that was about 12.5%. And semi-transparent meaning that while it absorbed the visible light, it was transparent to the infrared light, which then we stacked on top of the 17% SIG cell. 17% efficiency in SIGs being a representative number for what you could go out and buy if you purchased a SIGs module from a commercial vendor. And when we stacked the two together, we got about an 18.5% tandem, representing a moderate improvement over the SIG cell by itself. Now, the way I tested this was to separately test the perovskite cell and then separately test the silicon cell. And if you took no imaginative leaps, then when you make your module, you will also have to separately test the perovskite and the silicon, meaning you will have to have 4 wires leaving your module, and then you will have to have 2 inverters that are associated with that module. And the common argument against mechanically stacked tandems is if you have to do this, then you are adding significant extra complexity and cost to the system, to the installation, and that at the end of the day, you're behind from where you might have been with just a single junction cell. But that's not actually the case. There's a number of ways where you can string together your solar cells and end up with 2 wires leaving your module. The most obvious case is to simply string them all in series, and you can change the size of the perovskite solar cell so that you're current matching with the silicon. And then when you put the module together, you just have 2 wires. But now you have engineered in the current matching design constraint that was the Achilles heel of the monolithic tandem. So another option is to string together all of your silicon solar cells in series and separately string together all of your perovskite solar cells in series. And then when you go together to put the module together, then you hook those up in parallel, which means now you're voltage matched between the two. And this voltage matching is much less sensitive to the shape of the solar spectrum, and so you get less losses here than you would with the current matching. But now you've introduced some voltage matching requirements, and these are sensitive to temperature. So maybe the voltage of the silicon changes much more than the voltage of the perovskite as you heat it up or cool it down. And so the third option is to throw in some power electronics. And if you throw in some power electronics, then you can string up the cells however you might like, and this extra electronic circuit that you added in would correct for any mismatches that you might experience when you put this out in the field. Now I'm going to switch gears a little bit and talk more about how you make a semi-transparent perovskite cell. To make a semi-transparent cell, you need to have 2 transparent electrodes. And thankfully, when you buy your sheet of glass, it comes with transparent electrode already on top of it, so one of them is already taken care of. The difficult one is putting a transparent electrode that goes on top of the perovskite. And this is particularly difficult because the perovskite has a number of design challenges that you have to work around. First, because it has an organic molecule. If you leave the perovskite exposed and you heat it up to a moderate temperature, about 60 degrees C, given enough time, the organic will simply evaporate from your system and you won't have perovskite anymore. Another problem is that because the perovskite is made of salts and you solution deposited it, if you are not careful about the layers that you are solution depositing on top, if they're made of the wrong solvents or if they have water and are wet, then the perovskite can either be dissolved or undergo degradation. And so the initial solution that we came up with for this transparent electrode was to use silver nanowires. And silver nanowires are a transparent, highly conductive electrode. And if you've never seen them before, it sort of looks like you spilled spaghetti on top of your solar cell. And the solution that we came up with in order to make it compatible with the perovskite was to use a transfer lamination process. And so here, instead of spraying the wires directly onto the perovskite solar cell, we instead sprayed them onto a sheet of plastic. And so the sheet of plastic was exposed to high temperatures, it was exposed to the solvent, the alcohol solvent that we sprayed the nanowires from, meaning that when it was dry and when it was back at room temperature, now we can put it on the perovskite solar cell. And the strategy here now is that we're going to transfer the wires from the sheet of plastic and embed them into the perovskite. And we're going to do that basically by drawing our electrode onto the solar cell. And everywhere underneath this ball bearing where there is sufficient pressure, the nanowires will literally be pressed from the plastic into the solar cell. And so when we're satisfied with how much we've been drawing and we take away our sheet of plastic, we can see that there are no nanowires left on the plastic where we've drawn this electrode, and instead they are on our perovskite solar cell. And you'll see in a second, it doesn't look particularly transparent, and that's because these silver nanowires contribute some haze. But when you throw this into the spectrometer and measure what the transmission looks like, it's actually quite transparent in the infrared. So what we did here was to create a way to deposit a transparent electrode onto our perovskite solar cell that was compatible with the needs of the perovskite. But what we didn't do was stabilize the perovskite cell itself. Now, because there were this silver nanowire electrode was a mesh, that means there were a lot of holes between where there was actually metal. And where there are holes, all of the degradation mechanisms I mentioned before still prove true. So the organic can still evaporate through the holes in the metal, and the moisture from the air can still get in and degrade the perovskite. So here's a short little video just to illustrate what this looks like. Now we've taken a metal electrode-based perovskite solar cell and put it on a hot plate. And the perovskite is brown when it's actually a perovskite, but as you heat it up, it turns yellow. And yellow is the color of lead iodide, meaning that there's no organic left in your system and you no longer have perovskite. So this is a good visual example of what this looks like when it happens. So we needed now a transparent electrode solution that both was compatible with the deposition requirements of the perovskite, as well as stabilized the final solar cell that you make. And the transparent electrode we came up with didn't require a whole lot of imagination. ITO is the standard industry transparent electrode, and it's ubiquitous. It's in all of your touchscreen devices. And it's already well known for its ability to block moisture in its gas form. What was difficult was that the way you deposit ITO is by sputtering. And sputtering is an inherently damaging process if you're going to try and sputter onto an organic layer. And the perovskite itself, and usually the heterojunction layers on either side, can be considered as organic layers. So in order to avoid damaging the perovskite and its organic heterojunctions, we deposited by solution a layer of oxide nanoparticles. And these oxide nanoparticles provided a buffer in between the sputtered ITO layer and the sensitive organic layers underneath. And so we made a mechanically stacked tandem with this transparent perovskite solar cell as well. Again, about a 12.5% semi-transparent perovskite solar cell. And this time we stuck it on a 17% silicon solar cell, just to illustrate with that you can keep the texturing in the silicon solar cell that you would like to have there. And so the tandem that we made was 18% efficient, which is again a moderate improvement on top of the silicon solar cell by itself. But more importantly, what we made was a stable perovskite solar cell. And so here is an experiment that we did where we put a perovskite solar cell on a hot plate, and this hot plate was an ambient environment, so there was moisture in the air. And we illuminated the perovskite with a full spectrum lamp, meaning it had ultraviolet visible and infrared light illuminating it, and we operated it at its maximum power point over a period of time. And the red curve is the semi-transparent perovskite solar cell being operated at 100 degrees C. And between time 0 and time 10 hours, there was no measurable change as far as we could detect between the performance at those times, meaning that within the bounds of this experiment, we made something that was perfectly stable. This is in contrast to an opaque solar cell in black, which was also at 100 degrees C, and similarly as to the video I showed you a few slides ago, it degraded in a matter of minutes and completely stopped operating. Here's another video just to show visually how this ITO sealing works. This is a semi-transparent solar cell where this middle rectangle has ITO, and everywhere outside of this middle rectangle does not have ITO. And this is on a hot plate at 150 degrees C, and you'll see as time goes on, everywhere outside of the rectangle turns yellow, it's turning to lead iodide, which means the methyl ammonium is leaving, whereas the area inside the rectangle stays brown. It's still perovskite. I'd like to take a moment here now to acknowledge that while at Stanford we may have been some of the first to provide the existence proofs of these mechanically stacked and monolithic tandems, we're certainly not the only ones. And there's a lot of groups around the world who are doing really good work on pushing the efficiencies of both of these architectures up. And now there's over half a dozen papers on the subject. So now in the last part of the talk, I want to go back and address the question, does this get us from why not photovoltaics to why photovoltaics? And to do this, I'm going to make a couple of assumptions here. First, that we can make a 20% single junction perovskite solar cell in a large area module. And second, that we can make a 30% mechanically stacked tandem in a large area module. And we can do both of these things at high yield. And if we assume these things, and I think they're reasonable assumptions given the amount of people that are working in this area, then we can go ahead and do some cost modeling and decide what will happen in these scenarios. This is a process flow for a single junction perovskite module where everything, all the active layers are solution processed in an NIP style architecture, and the cell interconnections are defined as in a standard thin film cadmium telluride-like architecture.
And then, when we add up all of the step costs, we can arrive at a total aerial cost for the single junction perovskite module of $55 per meter squared, which if the perovskite were able to reach 20% efficiency in a single junction module, this would equate to 28 cents per watt. In this chart, I'd like to point out that all of the small columns in the middle have to do with depositing the perovskite and surrounding layers, as well as defining the interconnections between these cells, while there are three large columns that stand out on this plot. And these three large columns have to do with the front glass sheet, the back glass sheet, and everything else that is common to a module. Meaning that even though we have minimized the cost of depositing the absorber and surrounding layers and defining these cell interconnections, there is a price floor that we are reaching due to the necessary components of a module that at the moment we cannot do without. And the consequence of this can be seen in a direct comparison to cadmium telluride, which is the perovskite's closest competitor. Comparing cadmium telluride to the perovskite under apples-to-apples conditions, meaning they were both manufactured in the same place and produced the same efficiency, would save about 10 cents per watt from the cadmium telluride module. Since the module only costs 50 cents to begin with, saving 10 cents per watt is a significant amount. However, thinking back to the first slides, I told you that the total systems cost of a PV installation at the utility scale was $1.78 per watt. Meaning that saving 10 cents per watt on $1.78 per watt doesn't get us from why not photovoltaics to why photovoltaics.
And so the other option that we'll look at is to make a mechanically stacked tandem. And here we're using much the same process flow as before, except that in step 10, instead of depositing a metal, we'll deposit a transparent conductor. And we'll use this as the top glass sheet in a silicon module. And if we assume this silicon module is the DOE Sunshot 2020 silicon module, then it'll be about 20% efficient and cost $80 per meter squared. And if we take off that front glass sheet and we instead put on our perovskite coated front glass sheet, then we make a module that's about $105 per meter squared, and at 30% efficiency would cost 35 cents per watt. Now, of course, this is a bit more than the 28 cents per watt for the perovskite by itself, but that's not the whole story. And so here's a plot of the levelized cost of electricity for a number of different scenarios for solar panels. And the levelized cost of electricity is a number that encompasses the entire system over the entire lifetime of that system. And so this is a way to compare directly against other sources of electricity. And this horizontal line here at 6 cents per kilowatt hour is what the Department of Energy has decided is the target for the year 2020 in order to make solar more competitive with these other sources of electricity. And the top curve is, in an ideal world, what we could do today with the solar panels that we have today. And you'll see it's not there. It's not at the 6 cents per kilowatt hour that we need. And the curve right below it is what the Department of Energy would like for us to have in the year 2020, and at a reasonable degradation rate and under ideal conditions, you can reach this 6 cents per kilowatt hour target. The dotted line below it is the results of the cost modeling of the single junction perovskite that we did a couple slides back. And at 20% efficiency and $55 per meter squared, you can reach that 6 cents per kilowatt hour target and afford a significantly higher degradation rate than you could with the silicon. And so this is a clear advantage over the incumbent, but doesn't change the game in terms of choice between one and the other. But the bottom curve is a mechanically stacked tandem, where now we're assuming it's 30% efficient and $105 per meter squared. And for much of the degradation space that we're looking at here, you can get below 5 cents per kilowatt hour for your system. And so this represents a major change in the price of solar and can make it competitive with these other technologies. So to end, I'd like to leave you with a few final thoughts. I'd like to hope that I convinced you that the metal halide perovskite is an ideal wide bandgap semiconductor for use in tandems on top of silicon and SIGs, and that it's compatible with both monolithic and mechanically stacked tandems, but that these monolithic tandems have a couple of Achilles heels, and that the mechanically stacked architecture gets around these issues. And that there are signs that even though the perovskite has some stability issues, if you seal it properly, then you can make it stable against these environmental stressors. And that if you can combine all of these things into a high efficiency module that you can make at high yield, then we have a viable pathway towards getting, reaching this less than 6 cents per kilowatt hour LCOE target that we need. So thank you very much for listening to my defense, and I'd be happy to take questions.
I would like to ask the first question.
How are you going to edge seal them?
Which part?
The
whole
perovskites?
module?
Yeah, with the ITO, are you going to edge? I may have missed it, but like, is there
Yeah.
edge sealing?
So a common strategy when you're depositing things in a monolithic, defining cells in a monolithic style for thin film integration, you can put in an insulator that fills in these gaps, and that provides an edge seal for this cell. And then when you have a glass flat sheet, then you have to use something like a rubber seal for the module to seal that edge.
Colin, what would you say are the top 3 things you have to tackle to get to that 30% performance point?
Me personally, or the field as a whole?
Your personal opinion.
So I think the efficiency at a small scale is there. So one of the big things is to be able to make a 20% efficient perovskite cell that's on a couple meters squared of glass instead of on a little thumbtack of glass. Second one would be that since you're solution processing, there's a lot of dust in your system, and getting rid of that dust and therefore making this large-scale perovskite solar cell at high yield is going to be a difficult manufacturing challenge. So that's number 2. And then number 3, making a 20% perovskite solar cell, that's quite doable. But in order to get a 30% tandem, you need something that's highly transparent in the infrared. And so these semi-transparent solar cells I was making today are somewhere between 70 and 80% transparent. But if you really want to get up to 30% efficiency, then you need something that's more like 90% transparent. So working on the optical design of the perovskite stack in order to get 90% efficiency would be number 3.
Part of your modeling the module costs for perovskites, how are you doing that, like when we don't really know the degradation rate or the long-term stability properties? How are you factoring that into the cost?
So in this style of the cost, this is in dollars per watt. And when you say dollars per watt, you're saying dollars per immediate watt. So how many watts your module produces at time 0. So this doesn't take into degradation at all. When you're calculating LCOE, it does take into account the entire lifetime of the system. And so down here at the bottom is a function, you're seeing the LCOE function as a function of degradation rate. So if your perovskite is degrading faster, then you're further on to the right of this chart, and your system is more expensive.
How viable do you think it would be to use like a spectral splitter instead of having to go through the perovskite?
Yeah, that's a great question. There are a lot of papers that are using spectral splitting in order to make these style of tandems, and they are very efficient. There's some cases where the spectrally split tandem is upwards of 28% efficient already. The question is, how do you deposit, or sorry, not how you deposit it, how do you deploy it successfully in a low-cost manner? So now you actually have to have 2 different modules that are like orthogonal to each other, which is not particularly easy. And then you have to make a large area spectral splitter. And these generally exist in, they're pretty small, and you can buy them from Thor Labs, and they'll probably cost you like $100. So you can imagine if you're trying to make a couple square meters of a spectral splitter dichroic mirror, that you'd be paying That's a great question. A good follow-up experiment on this would be to measure the water vapor transport rate and the methyl ammonium transport rate through such a layer of ITO and calculate how long it would take for all of the methyl ammonium in your device to evaporate out. I don't actually know what that would be and whether or not that would be a problem on the 25-year life scale.
So you mentioned engineering cell areas in order to current match in the mechanically stacked tandem, but you also showed us a plot of how the solar spectrum changes even in the same place throughout the day. So commercially, would you have to offer this product in all different configurations based on where you're planning to sell it and how to deploy it?
Ultimately, I would not enforce a current matching restriction in the mechanically stacked tandem. I think that while this is a way for you to end up with two terminals coming out of your solar cell, it is a big problem, and that you should instead have some power electronics that corrects for any mismatch that you might have between the top and the bottom. But what you're mentioning is a very big problem in tandems, and if you were a concentrated tandem manufacturer, then you would have to provide a different product for your whoever was buying your system, depending on the location that you are deploying that product, which makes it very difficult to make concentrated photovoltaic systems.
The circle